Okay, now we're going to get to the really exciting part of NMR. This is where we get some of the most valuable information, the realm of spin-spin splitting. But before we do that, we are going to need to do a quick recap. So where are we and what have we learned? We have learned where NMR signals come from, that they're basically about little spinning magnets that can absorb radio frequency radiation, and that we can tell how many different sets of signals will appear in an NMR spectrum just by looking at the symmetry and the environment in which those hydrogens or carbons or whatever NMR active nuclei you're thinking about, where do they reside within this molecular glob of electron density that is a molecule. That position where the signals show up is called the chemical shift and is recorded in parts per million. And the chemical shift is determined by basically electronegativity, that's the inductive effects, and by anisotropy. Integration tells us how many hydrogens are associated with each signal, and I should note that integration only applies to proton NMR spectroscopy. It doesn't apply to other nuclei. And now, splitting, aka coupling. So spin-spin splitting is a result of the fact that these nuclei are really, really sensitive to what's around them. So the magnetic field that is around them, the so-called effective magnetic field, absolutely determines everything there is about how your NMR spectrum appears. So when you look at a molecule like this guy, okay, what we can see straight away is that we have two different kinds of hydrogens, red hydrogens and blue hydrogens, or basically two different sets of chemical shift equivalent hydrogens, the one on the carbon with two chlorines attached, and the ones on the carbon with one chlorine attached. They're clearly in two different electronic environments. So I have two sets of chemical shift equivalent hydrogens. Now, what does this mean in terms of how the NMR spectrum is going to appear? Well, here's the thing. What's kind of interesting here is that we will find out, of course, that there are two signals associated with the two kinds of chemical shift equivalent hydrogens. We will think about where they're going to appear. That's the chemical shift. And knowing that this guy has two strongly electron withdrawing chlorine atoms attached to that carbon, I'd say this is going to be further downfield than the blue ones. But now we're going to get into what's the pattern for each of these signals. We know there's two signals. We know they're going to show up in different places. But what are they going to look like? And here's the deal. That red hydrogen is actually a little magnet that is going to impact the magnetic field that the blue hydrogens feel. Alright, so keep that in mind. We have to now pay attention to all the magnets in the area, and hydrogens next door are little magnets. So if you think about that red hydrogen, and you think about putting this molecule in a magnet, and there's an effective magnetic field that all of the hydrogens feel, well, that little red hydrogen with its spinning nucleus could be aligned with the effective magnetic field, or it could be opposing the effective magnetic field. In which case, you see, if those blue hydrogens feel the magnetic moment associated with the one I just circled, that little tiny magnet that's aligned with the effective magnetic field, that's a slightly stronger effective magnetic field. And so the blue hydrogens will show up a little bit further downfield. But if I, circle now that guy, now remember, H sub A has an equal chance of being up or down. And so there's a whole bazillion of these H sub A's, red hydrogens in there. So there's some of them that are aligned with the field and some of them that are opposing the field. And the ones that are opposing the field, well, they are going to make the blue hydrogens feel a slightly less strong effective magnetic field because it's opposing that external field. Therefore, the blue hydrogens don't show up as one single signal. They show up as two, both equally high, one a little bit lower than the effective magnetic field, one a little bit higher than the effective external magnetic field. And so, actually, the chemical shift for these blue hydrogens is right smack dab in the middle because it got shifted a little bit lower and a little bit higher due to that crazy little spinning magnet right next door. That is an application of the N+1 rule. Simply stated, I have one hydrogen on the carbon right next door to my blue hydrogens. So I just go 1, 2. On the carbon right next door, there's one hydrogen. That's N, so 1 plus 1 equals 2. That means my blue hydrogens are going to show up as what is known as a doublet. All right, so the best way to understand the N+1 rule is to look at some examples. So the patterns are highlighted in this yellow box. If there's no splitting, it's a singlet. If it's split into two signals that are equally high, a 1-to-1, that's a doublet. A triplet is 1-2-1 in terms of height, and a quartet is 1-to-3 to 3-to-1. That's explained in detail in your text. So let's just look at some examples. How about this methyl ethyl ether? Well, first of all, how many different chemical shift equivalent hydrogens do we have? We have A, B, and C. All of these are in completely different electronic environments. This set of methyl hydrogens is really completely different from this set of methyl hydrogens. So don't think just because they're both methyls they have the same chemical shift. Different electronic environments. Okay? Now, let's spell it out like so and say, okay, let's start with C. Make that a C here. So these are all my little H sub C's. When I go 1 over, I can see that I have 1, 2 hydrogens next door. According to N+1 then, H sub C should show up as a triplet. And indeed, that's what we'll see, a 1-to-2 to 1 pattern for H sub C. Now we can use our correlation chart and predict where H sub C should show up, and it'll probably be about 1.1 part per million. Okay, well, now how about H sub B here? Well, how many hydrogens are one atom over for H sub B? Well, there's no hydrogens on the oxygen, so we get to ignore that. And we go over to the right now. So now here's our next door neighbors, 1, 2. There's 3 H sub C's. So 3 plus 1 equals 4. This is my kind of math. That means that the H sub B's will show up as a quartet, 1-to-3 to 3-to-1. That's a quartet. This is a triplet. And how about, finally, this guy? This guy, go 1 over. There's no hydrogens attached on the atom next door. So the N+1 says 0 plus 1. That methyl group will show up as a singlet. So if I want to predict the NMR spectrum for this guy, I should predict a pretty far downfield singlet for that guy, an even further downfield quartet for that guy, and a reasonably high upfield triplet for that methyl group. Probably around 1, probably around 3.8, probably around 4.2. And that's what my NMR spectrum, my proton NMR spectrum for that molecule should look like. Quartet, singlet, triplet. Alright, how about this guy? Alright, well, we again do the same thing we did in the first place. Identify the chemical shift equivalent hydrogens. So if I start putting all these hydrogens in, as usual, line structure is absolutely the enemy. So now I can see that I have H's all over the place. Okay, this is a highly symmetrical molecule. And in fact, I can split it right in half that way, I can split it right in half that way. What that's telling me is that I have A, B, B, C, 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 C. I only have 3 different kinds of signals. So, it's kind of a mess now. What kinds of patterns should I expect to see for those 3 sets of hydrogens? Well, my CH3s, if I go over, if this is 1, then this is 2, how many hydrogens do I have attached? There it is. I have 1 hydrogen next door. 1 plus 1 equals 2. Therefore, all of these CH3s should show up as a nice doublet. And that is not a nice doublet. That is an ugly doublet. But the point is a 2-line signal, both of them being the same height. Fine. Well, what about this guy? Well, that guy, how many does it have next door? Well, for crying out loud, it has 6. I've got 1, 2, 3, 4, 5, 6. So that's going to show up as something that's not even in the box. It's called a septet, and it's such a mess. That's what a septet looks like, only though it's really short and squatty, so you can barely see it. It's a 7-line signal, septet, and oftentimes you can't even see the very outlying peaks. Okay? So I have a doublet and a septet. Then what about finally these guys? Well, they're all chemical shift equivalent. And therefore, as we will soon learn, chemical shift equivalent hydrogens, they don't couple with one another. So they all show up as a single signal down in the aromatic region, probably around 7.2 or so. That's what my predicted spectrum for this para-diisopropyl benzene would look like. Alright, how about this guy? Alright, moving a little bit more quickly here so this doesn't last 4 hours. We have H sub A here, H sub B, H sub C, 3 different signals. H sub A has how many neighboring hydrogens? Well, I got nothing. There are no hydrogens on that next door neighbor. So H sub A is going to show up as a singlet, probably right around 1 part per million. H sub B, how many next door neighbors does it have? Well, it's got none here, but it has 2 there. So 2 plus 1 equals 3. H sub B is going to show up as a triplet, and that triplet should be down around 2.3 parts per million. I'll put it up here. Alright, now, how about H sub C? Well, again, H sub C has 2 neighbors. 2 plus 1 equals 3. So H sub C is also going to be a triplet. These two might be fairly close to one another. We'll say that H sub C is more like 2.5. I don't know. Look it up in your correlation chart. So what I should see for this particular molecule is a humongous 9-hydrogen singlet around 1, and then 2 triplets, probably pretty close to one another, more downfield in my proton NMR spectrum. Alright, and last but not least, what do we do with this guy? Well, because of symmetry, we know we have 2 different kinds of hydrogens. All 4 of those CH2s on the ends, and then the CH2 in the middle is unique in a different chemical shift environment. So I've got an H sub A and an H sub B. So H sub A is next door to 2 hydrogens. So H sub A should show up as a triplet. And H sub B is a true boy, that's a mess. A true pentet. You almost never see a true pentet, but their N invariably means chemical shift equivalent hydrogens, and there are 4 chemical shift equivalent hydrogens here. So that means that this is going to show up as a pentet. Alright, I'm going to stop this mini lecture now because it takes a lot of sinking in for you guys to really buy into this splitting stuff. So the best thing to do is just dream up examples and predict the spectra, and we will pick up this mini lecture in a separate continuation.